Today we're going to talk about related rate problems. Related rate problems are problems in which we're looking at how one quantity is changing with respect to time based on how a bunch of other quantities within the problem are changing at that given instant as well. So we'll just quickly go through some of the steps we're going to be going through as we do these problems, and then we'll do a few problems, and then we'll be done with the unit. So it's really important that you actually read and understand what's going on in the problem when we're doing related rate problems. If you don't understand what's going on, if you can't identify which variable you're trying to find the rate of change for, you're not going to be able to solve the problem. So figure out which variable you're looking for the rate of change of. And normally I write that off to the side. Then we're going to draw a picture of the situation that's going on and label the important things to the problem. We may be given some extraneous information. You can kind of just ignore that sometimes. But it's good to write down all the things that you are given. Very important that as you label things, you only label quantities that are constant as that constant. Okay? If you're looking at something from a distance of 100 meters and that distance is changing, you cannot label that as 100 in your picture because that's going to end up messing up your equation that you end up writing. You need to label that as a variable. So anything that's changing has to be labeled with a variable. And then off to the side, you should list off all the rates of change that you are already given in the problem. Once you've got your picture and you got it labeled and you've listed all your rates of change, you're going to want to write an equation to relate the variable whose rate of change you're looking for with all the other variables with the rates of change that you already know. At that point, it'll be time to actually do the calculus part, which is the easy part. You're just going to differentiate both sides of the equation with respect to time. And these will always be done with respect to time. That means that you're going to have a bunch of variables that are not t in the equation, but you're going to differentiate them with respect to t. That means you need to use implicit differentiation. Once you've got your derivative, you'll substitute all of your rates of change and all the other values for the quantities that were not constant, that were dependent on time. You'll put those into your derivative, solve for the one you're looking for, and remember units at the end. And remember on the AP test that if the question says indicate units of measure, it means that there is a point associated with the unit. So definitely don't forget it in that case. So let's take a look at this first problem here. We've got a hot air balloon that's rising straight up from a level field. So here's my hot air balloon, and it's rising straight up from a level field. I'll indicate that it's rising straight up with a right angle, and I can label that as a right angle because that angle is not changing. This balloon is rising straight up. It says we're tracking it from a distance of 500 feet directly west of the liftoff point. So we're standing over here watching this balloon rise and tracking its movement. The distance from where the balloon lifted off to where we're standing is 500, and that distance isn't changing. We're not moving, and the place that the balloon lifted off from doesn't change. So that 500 feet is a constant. We can label that in our picture. And it says at the moment the angle of elevation from the tracker to the balloon is pi over 4. The angle is increasing at this rate of 0.14 radians per minute. So I'm going to draw a line from the tracker, us, to the balloon. And we've got an angle here that it's talking about. And it's talking about that angle being pi over 4. But we can't label that angle as pi over 4 because it says the angle is increasing, which means that that angle, that quantity is the changing value. So we'll label it as a variable. I'm going to use theta here in this case. So we've got an angle theta. And we know that at the moment we're interested in, theta is pi over 4. So I'll just put that off to the side there. And I also know that that angle is increasing at 0.14 radians per minute. That's a rate of change of theta. It's a change in theta with respect to time. So I'll also put that off to the side. And then the final thing it tells us is that we want to know how fast the balloon is rising at that instant. Well, the speed or the velocity at which it's rising is a change in this distance right here. So I'm going to call that distance, just since it's vertical, I'll call it y. And we're looking for the rate of change of y with respect to time, which should be dy dt. From there, we just need to write an equation that relates theta and y and probably uses that 500 in it. And then we'll take the derivative with respect to t. So oftentimes, one of the things that you'll use here is some right triangle trig. And hopefully we can see that the tangent of our angle theta is y over 500, being opposite leg over adjacent leg. We'll multiply by the 500 to give us 500 tangent theta is equal to y. And now we're ready to take our derivative with respect to time. So when we take our derivative with respect to time, we ought to get 500, and then the derivative of tangent is secant squared, so secant squared theta. But because we're doing this with respect to time, we have to multiply this by d theta dt. And on the right-hand side, we just get dy dt. So now all we need to do is plug in our known quantities, this pi over 4 and this 0.14 for d theta dt, and solve for dy dt. And one thing to quickly note is that our units here are radians per minute, and our angle is given in radians. So we don't have to do any conversion. But if you were given something in degrees, you would need to change that into radians. So now we'll plug in our values. We've got 500 secant squared of pi over 4 times 0.14 is equal to what we're looking for, dy dt. And I'm just going to do this off to the side. We know that the secant is 1 over cosine. So if we don't remember what the secant is, and we're looking for 1 over cosine of pi over 4 squared. Well, the cosine of pi over 4 is root 2 over 2. So in order to find the secant, we just take the reciprocal of that, right? This is 1 over root 2 over 2 squared. Well, if we take the reciprocal of that, that becomes 2 over root 2 squared, or, well, 4 over 2. So just 2. So the secant squared of pi over 4 is just 2. So we've now got 500 times 2 times 0.14 is dy dt, leaving us with the final answer of dy dt is equal to 1,000 times 0.14, or 140. And our units were in feet. Everything was in feet, and it was per minute. This will be 140 feet per minute is how fast that balloon is rising up from the ground. In this next problem, we've got a police car approaching a right-angled intersection from the north, and it's chasing a speeding car that has already turned the corner and is moving east. So I'm going to real quickly just sketch out that right angle. So we've got a police car that's coming from the north, so from up here. It's moving towards this intersection, going this direction. And we've got a car over here that's going this direction. It's already turned the corner, and it's somewhere over here. It then tells us that there's a time when the police car is 0.6 of a mile north, and at that same time, the speeding car is 0.8 of a mile to the east. So what we do know, though, is both these cars are moving, and so neither of those quantities are constant. So we can't label this as 0.6 because that is changing. So we have to give it a variable. We'll call it y. And the same over here on this side, we can't label that as 0.8 of a mile. We'll label it as x because that quantity is changing as well. The next thing that it tells us is that the distance between the two cars is increasing at 20 miles an hour. Well, the distance between the two cars would be, looks like the hypotenuse of a right triangle. And first of all, we don't actually know what that distance is, but we also know that distance is changing, right? Because as this car moves down here, it ends up here, and this car is moving this direction, clearly the hypotenuse of that right triangle is changing as well. So we couldn't label that with a value. Anyway, we have to label it with a variable. Let's call it Z. And I'm going to off to the side over here note that we know that dz dt is 20, because it says that that distance is increasing at 20 miles an hour. It also tells us that the police car is moving. That was the one that's going to the south over here, right, coming down this direction. It says that that is moving at 60 miles an hour. So we might be inclined to say that dy dt is equal to 60, but that's actually not correct. We have to think about how y is changing. Right? This distance between where the police car started and the intersection, as that police car moves down to here and then to here and then to here, let's say, that value of y is decreasing, which means that the rate of change of y has to be negative. So it's very important that we make sure that's a negative 60 for dy dt. And then it's going to ask us here, what is dx dt? It's asking what is the speed of the other car, that speeding car, that same instant. So we're looking for dx dt. So seems like the easiest way to relate all of our variables here is just using the Pythagorean theorem. X squared plus y squared equals z squared. And we've got two options here. One of those options is just to immediately take the derivative. So I'm going to do that. We end up with 2x dx dt plus 2y y dt equals 2z dz dt. So that's one of our options. The other option is, because, well, we'll talk about why we might look at both options. One is that off to the side here, we know that the value of x is 0.8 at the instant we're interested, and the value of y is 0.6, but we don't actually know the value of z. And in this equation right here, this part of it, it says 2z dz dt. We need to know the value of z, so we'd have to go back in to our Pythagorean theorem and actually find the value of z. Now, another option, if you don't want to do that, is we could come down here and just say z is equal to the square root of x squared plus y squared, and take a derivative, dz dt is equal to 1 over 2 root x squared plus y squared, using the chain rule on root u, times 2x dx dt plus 2y dy dt. So we could go about this problem in either method. And we'll note that this second one, we don't actually have to find the value for z. So either way you want to do it is fine. We're actually going to take a look at how to do this both ways. So before we do that, let's see what z actually is. If we have x squared, that's 0.8 squared, and y squared is 0.6 squared equals z squared. Well, 0.8 squared is 0.64, and 0.6 squared is 0.36. That gives us z squared is equal to 1. So we must end up with z equals 1. And so now that we've got all this information, we should be able to use either method to get the same value for dx dt. So let's take a look real quickly at how to do that. So our first derivative gave us 2x dx dt plus 2y y dt equals 2z dz dt. And we had values. We don't have the page up anymore. Hopefully I'll remember all these values correctly. We had x was equal to 0.8, so 2 times 0.8. And then dx dt is actually what we were looking for. And then we have 2y, where y was 0.6. And dy dt was our value of negative 60. And then we had 2z, where z was 1, with dz dt equal to 20. So we end up with 1.6 dx dt minus, then 2 times 0.6 is 1.2, and 1.2 times negative 60 ought to just give you negative 72. So we have negative 72 there, equals 40, or 1.6 dx dt equals 112, and if I don't know, there was 7 then, 112, and dx dt then when you divide just gives you 112 divided by 1.6 is 70 miles an hour. So that's speeding cars moving at 70 miles an hour. The police car probably needs to speed up to catch it. Now, if we chose to do this the other method, where we had dz dt is equal to 2x dx dt plus 2y y dt over 2 root x squared plus y squared, we can still just go ahead and plug everything in. And as we do that, we'll have dz dt, which in this case, dz dt was given to us as 20. So 20 equals 2 times our x value of 0.8 times dx dt, the value we're looking for, plus 2 times y, which was 0.6, times dy dt, which was negative 60, over 2 times root x squared plus y squared. Well, just a minute ago, we figured out what x squared plus y squared was. X squared plus y squared was 1. In fact, we were trying to figure out what z was. And so we just have 2 times 1 down there. And as we simplify this down, we've got 40 equals 1.6 dx dt, well, minus 2 times 0.6 times negative 60. And we just did that a second ago, right? So 1.2 times 60 is that 72 value. And so we can see this is the exact same equation we had on the previous page. We'll add the 72 and divide by 1.6. Give us dx dt is equal to 70 miles per hour dx dt. So whichever method you choose to use, it doesn't really matter. You'll get the same method. We're going to look at one more related rate problem here, and then we'll be done with the unit. So we are given water flowing into a conical tank in a rate of 9 cubic feet per minute. So the first thing we'll probably notice here is that this is cubic feet per minute. It's telling us that this water is flowing into the tank. That's going to indicate those units, cubic feet, that this is a volume. So I'm going to note that dV dt is equal to 9. And because the water is flowing into the tank, the volume is increasing. So the volume here, the change in the volume is going to be positive. If we had water flowing out of the tank, it was leaking out of the tank, our dV dt would be a negative 9. So then it says the tank is oriented with the point down. How it stays like that, I have no idea. And it has a height of 10 feet. So let me just draw the height in. And that height's not changing. The height of the cone itself is 10. And it also says that it has a radius of 5, which is also not changing. Now, what is happening, though, is that water is being poured into this tank, and the water level is increasing, right? So this height right here is changing. I'll just label that as H, even though it's telling us that the point we're interested in is when H is 6, when the water is 6 feet deep. So I'm going to make a note off to the side that at the point I'm interested in, H is 6, but H is changing in my picture, so I can't label it as 6 yet. And then we've also got a little radius for the bottom piece of our cone where the water's spilling out. And so that's all that's given to us. And we'll note that we have a rate of change of volume, which means we likely need to use a volume formula for the cone. So this will pop up often enough. You should memorize it. The volume of a cone is 1/3 pi r squared h. And we'll note that since we're doing this with h equals 6, it might be convenient, in fact, it would be very convenient, if we had our volume equation written all in terms of h instead of including an r in it. Which means we're going to have to find some way to relate the radius to the height of this cone. So hopefully we remember back to some of our geometry. This is a right angle, and this is a right angle. And the two triangles that I'm going to look at here are both sharing this angle at the base. Right? So I've got one triangle that is a right triangle made from there, right from the full cone, and another right triangle made right here. Maybe I'll do that in a different color so we can see a little bit better. We'll go with the pink color here. This right triangle. Those are similar triangles. They share two angles. One is this one in green down at the bottom here, right here. They both use that angle, and they both have a right angle. That's angle-angle similarity, which tells us that the ratio between the radius of the full cone to its height should be equal to the radius to the height of the smaller cone that's made by the water filling up. And then we can figure out what r is equal to. If we just multiply by h, we get r is equal to 1/2 h. So we can go in and replace our r value with 1/2 h. And 1/2 squared is 1/4. And 1/4 times 1/3 will give us 1/12 pi. And then we have an h squared times an h, which is h cubed. So we now have our volume formula for this cone, all in terms of h. So we're now ready to take a derivative of it with respect to t. dv dt equals 3 times 1/12 is 3/12, which is 1/4. So 1/4 pi h squared dh dt. And the only thing that's in this equation that we don't know is dh dt, and dh dt is what the question was asking us about. How fast is the water level rising? So we'll plug in 9 for dv dt. We'll plug in 6 for h, and we'll solve for dh dt. I'm going to multiply this 4 over to the other side. That'll give me a 36. And then I've got a 6 squared here, which is also 36, that I'm going to divide by. So really, I've just got 1 equals pi times dh dt, or dh dt is equal to 1 over pi, and our units were in feet per minute. So we get the rate of change of the height of that cone of water is 1 over pi feet per minute. And so as we work through some more related rate problems, when you do them on your own, keep in mind the ideas of similar triangles, keep in mind Pythagorean theorem, keep in mind all of your Pythagorean trig work, all of the like right triangle trig, all of those formulas. They're going to pop up pretty often. And we're going to have a lot of varying formulas for volumes and surface areas. So you got to be careful that you get the right volume and surface area formulas, just like when we were doing our optimization problems. If you end up with the wrong formula to start with, then there's no chance you're going to be able to get the right answer. So that's it for related rates, and that's it for our unit on applications of the derivative.